Okay. Last time, I tried to give you guys some introduction to seismic processing. Uh, it's uh, it's just an addition to the mentorship section. I didn't want to just jump into interpretation, so that some of you will have an idea, or you guys will have an idea of what processing is all about. Because when you get to the industry, fresh from school, the concept of processing is something that most times you don't know about, or you've not heard of, or you don't get to hear. For us in especially trend here back home here. So I just wanted to bring it to bring the processing to you, so you have a bit of idea about it before we go into interpretation. So can you confirm you can hear me? And you can
Yes,
also
I can.
see my screen.
Yeah, I can see your screen and I can hear you.
Okay, okay, good. So we last time I gave you an overview of the introduction to what processing is. Told you the aim is to get an interpretable image of the subsurface. So on your data that you acquire from acquisition in the field cannot be interpreted. So it needs to go through some computer algorithm and workflow. So it will take a while. Processing takes sometimes, depending on the size of the data, between 3, 6 months, even 1 year or more to process one data set, seismic data. So depending on the size of the data and the type of data anyway, and also the objectives. So the primary aim to get an interpretable image of the subsurface. So ideally, the acquired data in the field looks like that. In the image on the left, the raw shot gather. And then when processed, the aim is to get a stack section of the subsurface. Okay, or stack sections of the subsurface. So I told you in processing, your aim at getting an accurate geometry. You have a compact wavelength and a data with a high signal to noise ratio. And I try to show you, give you this a little assignment to do so you understand the concept. When you talk about signal to noise ratio, you know what signals are or your primaries and how to identify them on a typical short gather or your CMP gathers. And I gave you this little assignment to do. I hope you attempted that. Then I showed you a typical workflow for seismic processing, mostly for land processing. Uh, this workflow, this is not an all-conclusive workflow, but this is the basic processing steps that must be done. In between, other processing steps may come in, depending on the processing objective, okay, and the data set in itself. But no matter what, these are the primary processing workflow or steps to be taken. So if we start going to every other processing step and details, we are not going to be done even in 1 month. So told you about the geometry updates. This is about the first step. After you load your seismic data that comes from the field, either in SecD or SecY format. I took time to explain what SecD and SecY format means. The data will either be brought to you in a tape cartridges or a hard disk, and you have to read them into or download them into your server. your computer servers, and then keep the original tapes as your backup. Then you have your SPS file as one of the deliverables from the acquisition, and told you the SPS stands for Shell Processing Support, and contains the S, R, and X file, that's receiver, source, and cross-reference files. And these files are required to do your geometry update. So this is typically what SPS files look like. They look like they are spreadsheets anyway, containing coordinate information and all that, elevation information and different other informations in the seismic data. The spreadsheet is wider than what you have on the screen. I'm only showing the far right end of it. If you have it, you need to scroll through from left to right and up to down. So it's a very large data. So I also told you after you do your geometry updates, you come up with your information of your data. One of such information is the source receiver map shown in the screen. You can see the source line, sorry, the receiver line on green, and the source short point and the source line on red. You also get your fold map, elevation maps, and all the rest. So I just show these two. So these are some of the information that will come up after you do your geometry update. Okay, and there are two ways you quality check your data to know if you got the geometry update correctly. Either you do a linear move out check, or you do a mute check. So for the linear move out, you flatten your seismic data using a particular linear move out velocity. Usually a low velocity move out, maybe 2,000, 1,900, depending on the basin anyway. So what you're using in Niger Delta may not be applicable, may not flat out your gathers if you have a data from Anambra Basin or any of the older sedimentary basins in Nigeria. So for the Niger Delta, most times when you do linear move out application, you may be using velocities about 1,900 to 1 or 2,000 meters per second. And you get your gathers flattened out and you know you did the job right. Secondly, you look at your mute, you apply mute on top of your seismic on your CMP gather, and then output the mute or display the mute on your short gathers, and this is what it will look like. So your mute lines will look something like this, and if any deviation from this normal trend of your short gathers, then there is a problem with the geometry update. The next thing I told you was about statics correction. I told you there are two types of statics correction or statics errors in the data, elevation statics and refraction statics. And I told you the elevation statics comes because there are differences in elevation of the geophones or the receivers, especially on land. And also because, on the land, you have hills, you have valleys, you have some high areas and low areas in terms of elevation above sea level. And then your shots, they drill short holes and introduce the dynamite inside the short hole. So all these differences in elevation will affect your data, and you need to correct for that effect. Okay, and that correction is known as elevation statics correction. And so I try to explain that using this diagram as well, showing the receivers on different elevation and a common reflector in the subsurface that's supposedly a flat reflector. And then you have your shots gather following this trend that is non-hyperbolic. Okay, so you are trying to, maybe it goes this way, it's non-hyperbolic. So you are trying to correct the effect of elevation and make them hyperbolic. And so you will now get something like this, sorry. something that tends to be more hyperbolic. So that is that for elevation statics correction. So in doing that, you get a seismic reference datum, which is where you are an imaginary reference line where all the receivers will be placed in the data sets, okay? And we call it the reference datum. So it could be mean sea level. For the Niger Delta Basin, we normally use zero datum because we are close to the ocean, so we use the mean sea level. If it's data that is gotten from an inland basin like the Anambra Basin, Bida Basin, or Benue Trough, your reference datum will not be zero because you are some kilometers or some meters above sea level. So they will choose a reference datum uh, that is above sea level. Then I told you about the refraction statics correction, where you try to correct about for the effect of the low velocity layer or the weathered layer. So the weathered layer, which is this yellow section, sorry, reddish section, or what we call the lateritic cover in geology, it has effect on your data because the seismic wave, when traveling through them, tend to slow down. Okay, the weathered rock slow down the travel path or time of your time of arrival of the seismic wave. So we correct that using the refracted waves. You know, when you shoot the seismic or the dynamite, some of the wave will move between the low velocity layer and the bedrock. Okay, so there will be a refracted seismic wave, and these waves is what we pick out in processing through a process called first break picking. So the refracted waves are also known as your head waves. Okay, and they are the first waves you see on top of the seismic data this way, as shown on the red line on this short gather. So this first black event on the data is your phase break. Okay, they are the refracted waves, and they arrive faster than the reflected waves to the receivers. Okay, so that's why they are the first, and that's why we call them the first breaks. So during processing for land data, you have the first breaks, and they have to be identified on your data. So mind you, marine data have less statics problem than land data. They have their own peculiar type of challenges that has to be dealt with during processing. But 1 minute, please. But for land data, 1 minute, please.
Okay, sir.
Okay, sorry about that, guys. I'm so sorry.
Okay, sir, no
So,
problem.
okay, so with the first break, when we pick the first break on our seismic data, it's one of, in processing, this is one of the very tedious processing steps because you have to pick them, even though it's picked automatically. Current softwares will use auto picks. You do a design of your maybe kind of a machine learning design of the phase breaks, and then populate it through the data, and the software will pick the phase breaks, but the softwares are never accurate. So maybe they'll have like 90% accuracy or 95 or thereabout, depending on the quality of the data anyway. So you have to go through from shot to shot, looking for where the for software didn't do a proper pick, and then you correct it. So you make those corrections. So the first breaks are like this, okay? For a good first break, you have this one I labeled A. So other ones are first breaks that are not of very good quality. So if you're doing trying to do auto pick on them, these ones that the quality are not too good, the software will just, after picking it, you see a lot of errors. So you have to go through to correct them. And in the acquisition, you have a lot of shots, and have up to 10,000 shots, 20,000 shots, and depending on the size of the acquired area, seismic area acquired. So picking them, making this correction can take a while and all that. So it's one of the challenging processing steps, or in terms of repeatability. It's like you're doing something repeatedly, and so that most people don't like it, but it must be done, because the quality of your phase break will determine the quality of the statics correction that you will do. So even though you don't like it, or it's not a pleasant task to do, you have to do it, and you have to do it correctly or judiciously. So when you do your phase break, this event you can see, uh, you can see the phase break, the black line on top. So the red dots on them is where you have used the computer to identify them. And the one on the left is before statics correction, and the one on the right after statics correction. What it means, you are straightening out this abnormality on your seismic data. So if you pick your first break, this was picked with, I think, Green Mountain software. It looks like this: before, after, before, after, before, and after statics correction. Before, before, and after. Then last, after you do your first break, your statics correction, both elevation and refraction, you apply them on your stack section, and you have something like this. So before statics correction, after statics correction. So the idea is that after statics correction, your events will improve. Okay, you have improvement, event continuity in your data sets. So without wasting time, we get to the next thing. We discussed about noise attenuation. And I told you about noise, that they can be random, they can be coherent in your data sets. And the idea here is to attenuate the noise. And then anything you have on the seismic data that is not hyperbolic in shape is a noise. Even the first break we talked about in the previous slide is a noise, because we are not interested in refracted seismic waves. We are interested in the reflected seismic waves. So the refracted seismic wave is a noise, but is a useful noise in this concept, because we are using it to do statics correction. After statics correction, you don't need it anymore. It's no longer important to your data. So if you get your statics correction appropriately, you can attenuate them when you're doing noise attenuation, okay? And for your noise attenuation, there are different types of noise. And so for you to properly attenuate the noise in your data, you do a noise analysis, okay? And identify the noise types in your data sets, okay? So the first noise I try to talk about is the ground roll noise. I told you the properties of characteristics of this noise that have low frequency, low velocity, and high amplitude. So on your seismic data, they stand out very firm. They're the first things you see, and they are peculiar to land seismic data. In marine seismic data, you don't see ground roll noise, okay? You don't see them in marine data. So when I mean marine data anyway, marine data with streamers, not with nodes. Sometimes if you do node acquisition,
ocean bottom nodes. You will see some in the marine setting, they don't call them ground roll anymore. They call them the mud rolls. So they also appear, they can appear in your data, but not very serious marine data. And in the marine data, there are no static errors as you have in land data. Okay, but if you do acquisition with nodes, you can also do some kind of a statics correction, mild statics correction anyway. So for your ground roll attenuation, I told you they are low velocity, low frequency, high amplitude. So you can see them standing out firm in front of your data with their high amplitude and looking more like an isosceles triangle in the middle of your data. So when you attenuate them, they are off. And what happens is that your frequency on the right is boosted. The frequency spectrum on the right is boosted. When you remove this peak on the frequency spectrum is coming from the ground roll noise. This part, you can see the amplitude is very high, up to 200 decibels, against others having 50 decibels. So when you remove them, you see that the decibels of that high peak is off. So your decibel, other amplitudes become boosted. And when you can output the difference, which is this, and see that you only have your ground roll noise outputted. And other noises we talked about, swirl noise and maybe linear noises. You can see them being attenuated before and after on this slide. And then I told you about the multiples. So multiples are very common noise in your data sets, especially in marine data. They are very common and stubborn. And in your land data, they can also be present. In land data, they will be present mostly as interbed or subsurface multiples. But for marine data, they will be there as water bottom multiples and also as subsurface multiples and pegleg multiples. So they are just seismic waves that travel multiple times before being recorded by the receiver. Okay, so when they reflect from a particular boundary, they go out instead of going straight to the receiver, they find another interface or acoustic impedance contrast, hit it and come back downwards and keep bouncing like a tennis ball until they get to a receiver. So they are called the multiples. So they can be removed by different methods, the random, the multiple, the convolution, and surface-related multiple elimination techniques. And for this example on the screen, you have before the multiple noise and after the multiple noise, okay? So you can see the multiple were eliminated after, and this in the middle is the difference, okay? So if you look at the before panel, you see that looking at it there, everything is looking like hyperbolic. But this particular event is not actually an event from a geologic boundary. Okay, it's an event that is coming from reflection, multiple reflection of this water bottle. So you have to attenuate them. So if you're not conversant with the term multiples or you don't know about them, if they are not properly attenuated during processing, if you see them in your seismic stack sections after processing, you will go and start looking at them as an event, okay? So you'll be misled during interpretation. So that is the reason why I'm trying to throw some of these lights to you during in terms of processing instead of jumping straight to interpretation. So for this short gather, you can see you have these events, flat events that are looking like geologic boundaries, but they are not boundaries. They are not. They are multiples. They are mimicking these other events that are above here. So if you attenuate them, look on this panel on the right, they are gone. They are no longer there. So that is it for multiples. So generally after you remove attenuate noise from your seismic data, this is a typically maybe how your short stack section before noise attenuation looks like. And after you attenuate noise, you see the improvement in your stack section, an improvement in the spectrum. The spectrum is the small box on the left. what we call the frequency spectrum. So before, after, you can see an improvement in the broadband of your frequency spectrum. Before and after, before and after. So that's typically what happens. Then I talked about amplitude compensation, where I told you that when your seismic wave travels down from the source, as it spreads out away from the source, the energy attenuates, okay? And the energy weakens out due to one, spherical divergence, and I explained that. Secondly, transmission loss, and then absorption, okay? So you need to compensate for this lost amplitude, and that is why you do what we call amplitude compensation, okay? So you can hear stuff like spherical divergent amplitude, SDAC, okay? Surface consistent amplitude compensation and all that, okay? So before, after amplitude compensation, you have this on your shortcut. That is after you have attenuated noise. So the data will look like this. In the deeper part, it will look whitish or whitewashed. In the shallow part where the energy is stronger before it loses its power, the amplitudes are higher. So you spread out these amplitudes from the shallow part of your data to the deeper part. So before and after, before, after. And on stack section, you have it before, after, before, after, before, after, before, after. You're balancing the amplitude throughout the data. This step is carefully done, especially from noise attenuation and amplitude compensation. You have to be very careful because when you come to your interpretation, remember your DHIs, you're looking at amplitude differences. So during noise attenuation, you don't attenuate any of the hyperbolic signals because they are containing geologic informations. And during amplitude compensation, you have to be very careful to balance them or compensate them without doing it too much or too little, so that when you finish your work, every amplitude will be properly balanced across the stack sections or the seismic volume. And then you can do your DHI, all those your bright spots, dim spots. Those things can be destroyed by processing. So your processor has to be very careful not to destroy the amplitude of the seismic data. This is another stack session before and after, before, after, before, after. So the next, I think this is where we stopped. So we are going to talk about the convolution today. This is a very important seismic processing step. From the geometry update to where we are now, the amplitude compensation, some people will term it the pre-processing. Anything you're doing to prepare the data for the convolution. And another name for the convolution is signal analysis, because at the convolution stage, you're trying to look at the seismic signal. Okay, so what is the convolution? Okay, before that, we want to talk about convolution from the term deconvolution. So the first thing that happens when seismic energy is generated and transmitted and reflected is convolution, okay? So the convolution is like reversing the process of convolution. So convolution is a mathematical operation defining the change of shape of a waveform, okay, resulting from its passage through a filter. And what is this filter? The ground is the filter. So your seismic wave, when they pass, you remember that when we did our seismic method, we said when there's a reflection, we calculated reflection coefficient, and what did we generate? A spike. Or we had this, we have something like this. Positive reflection, we did something like this. Negative reflection, we did something like this. Positive reflection, negative reflection. These are your spikes. And this is what actually is happening in the subsurface, okay? So the process of this seismic energy moving through the filter, which is the Earth subsurface or the subsurface rocks, the seismic energy is being altered. Okay, remember that when we finished this, I told you to generate a trace, and you did something like this by yourself. You convolved your spike, something this way. Now, this convolution process Remember, the seismometer, or what you call your sensor, your receivers, is recording both the reflection and the noise. So the shape of this your convoked seismic data or your trace depends on the noise, not just on the reflected waves, but also the noise input, their shape. Okay, so when your seismic wave is traveling through the rocks, we already know about up to the reflectors and the reflection coefficients. We do a convolution, okay? We convolve all the spike endpoints or our reflection coefficient points. We add them up to generate a trace. If you introduce the noise that's also recorded by the geophones, this is what we'll come up with. So a product, our seismic trace is a product of both our receiver reflection signals and noises, okay, or reflected waves and also the noises. So at the end of the day, this is what we have. So in a convolution process, you have the whole response, both noise, both signals, they are all recorded. And this is a typical mathematical expression for that. So what you have recorded in your seismic data includes both your basic wavelets, okay, W in time, your noise in time, and their ambient, your noise in time too, N, and then the Earth impulse response is your primaries, and even your multiples, okay, all recorded into your data. So your waveform or your wavelet is your trace that you generated at the end of the day. So at the end of everything, you're trying to do a deconvolution of by getting back the original seismic inputs that came from the source. So this schematic diagram also shows you the convolution process, your seismic wavelets as they travel and they reflect. And this is your reflectivity series in terms of your reflection coefficients. And then this is what you get at the end of the day, the seismograph. Okay, so the convolution is from you moving back from what you have in the seismograph or your receivers back to what your reflectivity series is. What do you mean by your reflectivity series? What your reflection coefficients that we use to generate our trace, what it recorded initially before it was the data was affected by noise input and all that. So therefore, the process of doing the convolution simply means that you're trying to what? Restore the seismic, the original waveform, okay? You're trying to restore them to that original reflectivity, which is your reflection coefficients, okay? Before it was tampered by noise input and all that. So there are different ways you do the deconvolution processing called the surface consistent deconvolution, predictive, wavelet, spiking deconvolution, depending on the software or the processor and what you choose, and especially the data sets, because you test different deconvolution steps or processes or methods rather. Anyone that suits your data best, you can choose. Then what is the effect of doing the convolution? Okay. When you do the convolution on your data, you are going to compress the basic wavelets. You're going to attenuate the multiples in the data because the convolution helps in multiple attenuation and the reverberation attenuation. Then the resolution of your data will be improved after the convolution. So remember when I showed you that initial stack section, that one is good processing, one is great processing. The one with a great processing had a better deconvolution done on it because the events are, I told you, if you remember my description, I said the second image looked like it was drawn with a sharp pencil, while the first one was looking like it was drawn with a blunt pencil. So these are the effects of deconvolution. Your deconvolution will compress the wavelets. Okay, so this is what we also mean. Then also when you do the convolution, your frequency spectrum is expected to improve. Okay, your frequency spectrum. So this is frequency spectrum before the convolution. After the convolution, you have a broadband spectrum. So there will be an improvement in your frequency spectrum after the convolution in frequency domain. In time domain, you have what you have is a compression of your wavelets. So you have initially in time, if you look at your data in time domain, initially you have like 3 wavelets, okay? But when you do a deconvolution, they are compressed, okay? Looking more like 1 wavelet. So your data becomes sharper and the resolution improves. So this is what I mean for surface consistent deconvolution on a short gather. I just zoomed into this particular short gather. Look at before and after. What do you see? You see that the lines or the events, the hyperbolic events, they are looking broad, but after the convolution, they become thinner. So what happens? You have deconvolved the data, you have compressed the basic wavelets, and the resolution of your data will become better off. So how does it affect you in your interpretation? If the seismic data is not properly deconvolved, the convolution wasn't properly done, 1, you will not attenuate some of the multiples in the data. 2, the resolution won't be that sharp. So if you're mapping a horizon during interpretation in a data with a poor deconvolution job done, at a point you'll be confused between 2 events or reflections. You don't know which way, where is this? You get to a point you'll now be wondering, is this where I should map the horizon, or is it not? Is this event correct or is not correct? But with a properly deconvolved seismic data, the events are sharper, resolution is better, so you can map your horizons with more confidence. Okay, so when you look at it on stack section, this is also what it looks like. The shapes of the geology of the area will not change, but you look at the events properly, you find out that they look better compressed. And if you look around this interval and so look at the same interval from here, you find out that these events are better continuous on the after display. So the event continuity is improved, resolution is improved. Moderator, have we gone 1 hour? Check the time for me.
No, 47 minutes.
Okay, that's good. So we can finish. So if you look at also the spectrum, the frequency spectrum, this one, the box here, you see that before the frequency spectrum looks thinner, but by the time you do a deconvolution workflow, your frequency spectrum becomes improved. What it means is that the higher frequency data, you can see the frequency broadband here is between here and here. That is your dominant frequency in this data. So whatever the figure here is in terms of reading, maybe from 20 hertz to 50 hertz, that's your broadband before the convolution. But after the convolution, you look at it, you see your dominant frequency is between here and here now. So you can see the data, the frequency spectrum is improved maybe from 20 to maybe 75 hertz. So you can see that effect after the convolution. So when you are in a place, they are doing the processing for your company, and they are doing their deconvolution process. This is what you look out for. The frequency spectrum before and after the convolution, and how compressed the basic wavelets will be. Okay, and there's another QC. I don't think I added that what we call the autocorrelation. I think that will be 2-way higher up beyond this class. So that's another way to QC the convolution job. So the next thing is velocity analysis. So after you do a deconvolution, you do a velocity analysis and stacking. Okay, what do I mean by velocity analysis? Remember that when we talk about the common midpoint, that when you have a common midpoint here, it means all the receivers that are imaging this particular spot. So for us to do a velocity analysis, we normally bring our data to the CMP domain. Okay, common midpoint gathers. Instead of using the short gathers, we are no longer dealing with shorts. we'll be dealing predominantly with CMPs. So what you have in CMPs are almost similar to what you have in shorts, but you're just looking at the data in terms of CMP. So this could be your CMP1. CMP, that's meaning this particular CMP or this spot will become CMP1, another spot CMP2, and others throughout the data. The result in your CMP will look like the result in your data because at the end of the day, you also have hyperbolic shapes. So if you are to record this image in terms of time, like the previous assignment I gave you, in terms of arrival time to these different receivers, you can see that the short points are increasing away from source 1 to source 5, and then receiver 1 to receiver 5. So if you look at the arrival time from short 1 to receiver 1, short 2 to receiver 2, the arrival time of the seismic wave keep what? Changing, even though their common midpoint remains constant. So if you also plot that on a graph, you get a hyperbolic shape. Okay? You get a hyperbolic, somewhat hyperbolic shape like the one I'm showing you here. So what does that mean, or what does that imply? Remember that your velocity is equal to distance of travel over what? Over time, right? And you have your offset, okay? You have your offset, and then you have your distance of travel of the seismic wave where it made it, and then you have the time, okay? So your time here is your two-way time from receiver 1 from short 1 to receiver 1. So you have your two-way time, and then the distance of travel is the offset between receiver 1 and short 1, okay? That's your offset, and that's your distance, okay? So what is missing is, your receiver or your geophone, for instance, have already recorded the two-way time, okay? And you on the field, when acquisition was done, you have already recorded your offsets in terms of, the offset of this data, minimum and maximum offset. So what is missing is the velocity. So what is the velocity that this seismic wave used to travel from a particular short point to a particular receiver point? So you know the basic mathematics. If you make this the subject of formula, blah, 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 you put your offset. And so this is typically what does the software. You're not doing the calculation anywhere, but you're going to produce this velocity with which the seismic wave used to travel through the subsurface. So this is typically the background of what the software will be doing. So your data already have offset information, D, and it has the two-way time in terms of time, T. So you're trying to generate the velocity. And if you get that velocity correct, you're going to flat out this event. Remember this event. Remember the event is coming from a somewhat flat geologic boundary, theoretically. And we believe that the seismic wave travel from the sources to the point and then reflect to the receivers. And because of distance away from each other, what we call the normal move out, okay? Because of distance away from each other, what we call the normal mover, we got at the end of the day, we get a hyperbolic shape. I explained that in previous class, and I gave you assignment on that. Okay, so the idea is that you're going to regenerate the velocity that the seismic wave used to get to this boundary or this midpoint. And if you're to do that, if you get that velocity correct, you're going to now reproduce this flat geologic boundary. Because if you get that velocity correct, this hyperbolic shape will flatten out. Okay, so that is what velocity is all. Velocity analysis is all about. Okay, so that's what velocity analysis is all about. Reproducing the velocity with which the seismic wave traveled within the subsurface, and you know that that velocity of travel is dependent on the rock type, because you know that the velocity, if this is sandstone, for instance, and this is shale, the velocity of travel in sandstone will be different from shale, right? So your velocity for this particular CMP that's here, the velocity for the point here, and let me change the color of my pen for confusion sake. So the velocity for this particular event, can I clean my slide? Discard, bring it back again. So the velocity for the first event A, okay, velocity for the first boundary A will be different for velocity for the second boundary B. Okay, so you know that A gave us this particular event here, and B gave us this event here on our seismic data. So on our short gather, our CMP gather, you have these events. They are hyperbolic in shape. I just drew one side of the hyperbola. If you complete the graph, you draw it to the left side. So I just have the right side of the hyperbola. So what it means is that you're trying to generate the velocity for the first geologic unit. Let's say this is sandstone and this is shale. You're trying to generate shale. You're trying to generate the velocity with which the seismic data travel through the sandstone and then into the shale, through the shale. And then if you get that correctly, you're going to reproduce the geologic boundaries A and geologic boundary B. So to do that, you need to do a velocity analysis. So the software is what you use to do that. Okay. So ideally, this is what you have the image on the far right. So in seismic processing, steps here by reflection events are flattened. In a common midpoint gather, it is referred to as your stacking, and then as the shots roll along, there will be so many receiver pairs in terms of your CMPs and your CMP locations. And then if you are to flat them out, you get a flat gather. So if you have the image on the right, for instance, you have the hyperbolic shape on the image on the right, okay? The first image I'll label A. And then on the one on label B, the hyperbolic shape has been flattened out. So you're using the normal move out correction and the velocity function to flatten out this event, the hyperbolic event. You're going to make them to become flat. So that is what velocity analysis is. Now, stacking in itself now means you're going to use this velocity function that you generated, or velocity values that were generated during velocity analysis, to now do a stack section and then build a model of the subsurface, which you call the stacks, your stack sections. Because you have gotten the velocity that flattens this gather. Remember, mind you, on the short gather, all these lines you're seeing represent different geologic boundaries. So on each of them, there will be a different velocity reading, okay? Or velocity will be picked on intervals rather. So you pick velocity on interval, we'll call the interval velocity. So if you have a CMP gather and the events are hyperbolic as shown on the left, okay, you already have the distance, we have the arrival time of these events. So you're trying to get the velocity that will make these events to become flat. So when you pick it on the software, it doesn't matter the software the organization is using, whether they are using ProMax or GeoEast or Reveal, it doesn't matter. They are all doing this fundamental thing. All the softwares are designed with this fundamental theory or principles. So if you pick the correct velocity, the event will become flat, as you're seeing on the image in the center here. Good. If you pick a velocity that is too slow, the event will be pointing downwards as if it's still hyperbolic in shape, okay? So slow velocity, the event will point downwards like it's still hyperbolic. When you pick the velocity that is too fast, the event will be pointing upward, just like this is also showing. So if I use a red pen to kind of mimic their part, the events. So when you pick it properly, you see the events are flattened out. So that means wherever horizon you are on, come on,
Hello. Yes. Or is it that I can't hear the mentor again?
Yeah, I can't hear you too. I can't hear him too.
Okay, let's give him a moment, please. Everyone should just hold on. Thank you.
Sorry, guys. Keep being interrupted. I've muted my phone. Sorry. So back to what we are saying. So if you keep picking the velocities, when you pick the right velocity, the gather will be flattened. When you pick the velocity that is too slow, the gather will still remain hyperbolic or somewhat nearly flat, but it will still be pointing downwards like it's still hyperbolic. So it will have this trend pointing down. And if you pick too fast a velocity, it will point upward this way. So if you're to be in a place they are doing velocity analysis QC, or they are doing processing for a company you work for, and they are bringing the data, your target is to make sure that the gathers are flat. Because when the gathers are flat, it means the proper velocity of that geologic unit or that boundary has been attained. Okay, remember that your seismic wave acoustic impedance is a product of velocity and density. So you don't have control over the density of the rock. What you have control over in processing and your data is velocity. Okay, you only get control over density when you do well logging, when you drill the well, gotten the well, rock samples or rock cuttings, and then you can have your density log. And then for at this stage where you're doing seismic acquisition process, you're not inside the ground. You didn't drill any well yet. So you don't have a control over density property of the subsurface rock, but you have a control over the velocity of those rocks, because it is those velocities that the seismic wave will use to travel through them. Okay, so you get the correct velocity, the gather will be flat. So the aim is to get your gathers to be flat. So this is what a velocity picking operation looks like. And on the left, you have your CMP gather. On the right, you have what we call velocity spectrum. And then this black spot is where you're picking the velocity. So you can change these spots, either you shift it to the right or to the left. If you're shifting it towards the right, you're increasing the velocity. If you look at the panel, on the top side is velocity from 1,000 to around 8,000. And vertically is time. So if you pick velocity, it means you're adjusting these black dots, okay, right or left. If you go right, you're increasing velocity. If you go left, you are decreasing the velocity. So when you pick it correctly, your gathers will become flattened. Now, a situation where you're picking and the velocities are not flattening out, then it means that something is wrong with the data, or there is a noise in the data, not wrong in the data actually. Let's say you're picking the velocity this way, and you still have some gathers that refuse to flatten out. It could be that you have presence of multiples in your data. Remember, multiples will mimic your gathers, the events of your seismic data. So in your short gathers, your multiple will also be there, like the events, or your CMP gather rather. Your multiples will also be there, but their velocities will be lower. The velocities of multiples are lower in your data. So they will tend to follow where I've marked with red color. And in your short gathers, you may not be flattening out the gather around the area where the multiple is very predominant. So that's the input of multiples in your data. So with that, you now know that you have to do a multiple attenuation technique. Maybe you do a radon the multiple or whatever multiple noise attenuation you want to apply. So stacking in itself now means summing up all your CMPs. Okay, remember that you have your different CMPs and you have a hyperbolic shape. And when you pick the right velocity, you're flattening out the CMP gathers, okay? Layer by layer, all right? You're flattening them out layer by layer, or in terms of strata by strata. So stacking means you're gathering all the CMP gathers
I'm producing one single super trace, okay, which is your stack section. So it is the stack section that you have, which is a summation of all the traces in your seismic data, and producing a single cross-sectional view of the subsurface. Okay, the sum traces are gotten from different shots recorded on with a common reflection point, known as the CMP. Okay, and after stacking, a single trace is formed with an improved signal to noise ratio. Now, one thing you must also know that in processing, stacking is a denoising step. After data is stacked, remember that to produce your stack, you need to be on the CMP domain. You know that in CMP domain, it is where you get your fold. Remember what I told you in acquisition. So the more the more receivers that are looking at the common midpoint, the more the quality of that, the higher the fold of that data, and it means the better the resolution of that data will be. And so when you do stacking of this common midpoint, you're going to have an improved data in terms of signal to noise ratio, especially if the fold of that data is high. So that is what stacking is all about. And then velocity analysis is also all about. So the next thing we'll talk about, which is about the last processing step, is migration. What is migration? Okay. This is a processing step where you're moving subsurface events to their true positions in the subsurface, or deeping events, moving them to their true subsurface positions. So all this while we've been describing with flat events. Okay, there you travel your receiver to your source, or your source to your receiver, however. Then we are trying to illustrate that using flat cartoons and flat events. But in geology, you know that the events in the subsurface are not all flat. Some events are dipping, okay? You have some rocks that are dipping to an angle, not just some, all the rocks. Most of them, most times, will have at a point where they dip to an angle. And so during acquisition, the seismic wave, just shown on this image, they will not actually image this dipping event appropriately in your gathers. Okay, they are your gathers and your stacks. When you image the data, this dipping event will not be properly represented. So your migration is a way of relocating the seismic wave, or making the seismic wave move all the dipping events to their true subsurface positions. Okay, so you have an accurate image of the subsurface, and it's very important because it will also collapse diffractions in your data, and it will increase your spatial resolution. When I say spatial resolution, resolution from left to right, horizontal resolution. Temporal resolution is improved by deconvolution. I've explained deconvolution. It improves your resolution vertically, temporarily. Okay, but your migration processing step increases your resolution spatially, that's horizontally, because you have the dipping events actually occurring in their proper subsurface position. What are these dipping events? You have faults. Faults are dipping events. You have your faults occurring this way in your data. You can have your rocks or the other lithologies horizontal, but faults will occur as a dipping event. Some geology your rocks will also dip with time, okay, across the survey area and all that. So you need to move these events to their true subsurface position. That's what migration is all about. So typically, before you migrate, this is a typical stack section: before migration, after migration, before migration. So before migration, what you'll be looking at, it will look more like an anticlinal structure, just like this, but in reality, it's not a true anticlinal structure. It's more like a thrust fault. Okay, if you look well, you'll see an amplitude change that shows a thrust fault around here. So it's you do your migration to increase your spatial resolution before, after, before, after, before, and after. So the event is better now, and the true geology is being represented after migration. So there are different types of migration. Migration is done in time and then in depth. Remember that your receivers are recording two-way times, okay? Two-way times. So your seismic data throughout the processing step process has been in time, in terms of from 0 time to maybe 6 seconds, 10 seconds, depending on the record length of the seismic data. So when you are still dealing with the data, when you finish migrating, sorry, when you finish your processing and you get to migration stage, you are migrating the data in time. And there are different ways you migrate. There is what we call the catch-off migration. There's reverse time migration and all that. Then after migrating in time, you have to also migrate. You can also migrate in depth. Okay. So when it's time migration, very important. When you want your data fast, immediately after your processing, you migrate in time, and the data can be you can start interpreting them. Okay. You are not in a hurry, so turnaround time is critical. Okay, you want some, you're kind of in a hurry rather. You want to get the data, you want to start interpreting the data, you want to start looking at the subsurface geology and all that. So when they migrate in time, the data is good. But your data is recording the subsurface with respect to time in terms of depth. It's not recording in depth, it's recording in time from 0 to 6 seconds, 10 seconds, 8 seconds, 4 seconds, as the case may be. But when you go to the field to do your drilling operation, you have to drill in depth. Drilling operation is in depth. Your well logs are in depth, but your seismic data is in time. So this is why during a interpretation, you do what we call the well to seismic tie, where you're tying the well logs, which are in depth, to your seismic data that is in time. So the seismic data migrated that is in time. Now, if you have a low velocity problem within the area where the seismic data is acquired, you can also do your time migration and then stop at time migration. But in most cases, companies will go into depth migration, okay? Changing the seismic data from time to depth. And to do that, depth migration gives you a more accurate information about the subsurface in terms of velocity distribution and other. Because if you have a place where the velocity variation is very strong, what I mean by velocity variation, in a place now you have a fault like this. Some of you are very conversant with this structure in the Niger Delta. These are two faults. Okay, these are two faults. So you have this rock unit, and then the rock unit is the same thing here. Okay, and in this part it's also the same thing. Okay, so this rock unit at level A is the same thing here, and it's the same thing here, A, and it's the same thing here, A. You can see that if you look at it laterally, there's a variation in geology. Now, another rock unit will be here, that will be labeled maybe B. So you have a B here, you have B here, and you have B here. So this is B, and this is B, and this is B. So these are different rock units. If you look at them in geology from left to right, you see that property of the rocks change. So if, for instance, you are going from because of these faults here now, let me change the fault color to green. So because of these two faults here, and maybe probably another fault here, if you have another fault here, you will also know that the geology will further change, because A here will further go down because the normal fault. What I'm trying to explain in essence is that now if you look at it laterally at this level, where I have the blue arrow, for instance, you know that this particular rock A has its own velocity and density, okay, which is acoustic impedance. And the same thing with this, okay? And the same thing with this. But if you come, B has its own different velocity and density property because there are two different rock types. So if you go horizontally from the point 1 to point 2, you see that geology is changing. By the time you encounter this rock, around this area, velocity is changing horizontally because you're moving from rock A to rock B, okay? And then from rock B, you're back to rock A. So you have encountered different velocities due to the presence of these two faults. Are we together?
Yes, sir.
Okay, because you have encountered the velocity changes due to the presence of these faults, and you know in the Niger Delta region, you have multiple faulting, that you have things like this in your seismic data. So you have your host and your graben kind of system, the growth faults and all that. So because of these complexities, you have strong velocity changes in the subsurface. So there will be strong velocity variations in the subsurface. And so for that reason, you need to do a depth migration. Also, in areas where you have salt diaparism, you also need to do a depth migration. And in the Niger Delta, we have what we call shell diaparism, okay? Also, it introduces a lot of velocity issues in the subsurface. So you need to do a depth migration. So another word you say when there are severe anisotropy. So you have a lot of anisotropy means change in velocity in different directions. And when you have less severe anisotropy, or where you have more isotropy, you can do your time migration. So that is that for the two types of migration types. So if you look at them in financial perspective, when you have less money to spend, you do a time migration. But you have to, if you go into depth migration, you're going to spend more money. It is more expensive to do when it comes to the economics behind that. Now, but this class is not much interested about the economics. We'll look at the panel on the right side. You can see the x-axis is telling us, sorry, the y-axis is telling us velocity variation, while the x-axis is telling us structural variation, okay? So if you have in a basin, and you have a low velocity variation and low structural variation within the basin, you can do a post-stack time migration seismic processing. What do we mean by post-stack? After you've done stacking, I've explained stacking, you can now start do a migration after stacking. Okay, but if you have a more increased velocity variations, just like we have in the Niger Delta, you have to do a pre-stack time migration. So post-stack time migrations are faster to do. You have already finished stacking the data, you now do the migration. They are quick, they are fast. If your velocity variations are not much, you can do that. But immediately you start having complex velocities and complex structural information, like you have like I showed you in the former slide in the Niger Delta, something like this, the cartoon I drew, you have to do what we call pre-stack. So in the Niger Delta, what we do is PSTM, pre-stack time migration, meaning before you stack the data, after you finish your velocity analysis, before stacking the data, you now do a migration on your common reflection point, CRO gathers. So you now do what we call a catch-off migration in your seismic data. Okay. If the velocity variation is more severe and the structural variation in the basin is also very, very severe, also like you have in the Niger Delta, as shown in the former slide, you then further do a depth migration. So that is the difference. That's what migration is all about. Okay. In migration also, there are other types of migration, reverse time migration, beam migration, multi-path migration, and wide wavelet migration and all that. So if you are doing the migration in the Niger Delta, for instance, The pre-stack time migration is straightforward. After your processing, you migrate in time. But for you to go into PSDM, as it's called, this is called PSDM. You must have a well control, okay? Some wells would have been drilled in the field and you collect some well information. This is PSTM. So you have to collect some well data in terms of your markers and your well. All of us in the field, so you may have the geology student would have heard of markers. Some of them call them biomarkers and all that. You get these markers as control. You now get your horizons that you have picked during the interpretation of the time that migrated data sets, and then bring them into your data and then do a depth migration. So during depth migration, well controls are used. You have your wells, and with these well controls, because on your wells, you have the real geology in terms of the real log information and the sonic log, which also gives you the velocities of these logs, of these rocks. So with that, you will be able to do your pre-stack depth migration and then get a better image of the subsurface. Okay, so this is what I mean by all those explanation. The image on the left is a time migrated seismic data. You can always interpret this data. It's already showing you the different structure in the data. You have your faults, your growth faults that are trending in opposite direction to each other. You have other faults that are also here. Okay, like this one and this one. You can also see all these things in your data. But by the time the data is migrated in depth, if you look closely, the image on the right, you can see that the data is better in terms of clarity. The fault resolutions are clearer in the image on the right. If you look at the shallow part, there is more event continuity and less random noise. In the shallower part of the time migrated data, there are a lot of random noise. Okay, but by the time you do a depth migration, the noises are less. Okay, if you look at this interval on your time migrated data from 2,700 milliseconds to about 4,000. If you look at it, you see that this particular event, look at where I put the arrow now, it seems that this event is tending continuously. You are not sure if there's a structure here or not. But if you look at it in your depth map or your depth stack section rather, your depth migrated data, you can see that there is a kind of amplitude change that looks like a vertical structure here on this data. But before, you are not too sure on your time migrated data. So that is the effect of your depth migrated data over your time migrated data. Improved data image, and you have more velocity constraints, which you have been able to resolve using your wells that were introduced during depth migration. So in terms of business needs, your migration depends on the stage of your business phase in the oil and gas industry. For instance, during the exploration phase, you can just do your depth migration and then go and start interpreting the data and start your interpretation and drilling operation, field development planning and all that. So at exploration stage, you do your time migration. Okay, after you interpret the data after time migration, you drill your wells and all that. Okay, and after that, if you want to do a further development phase in the field, after you drill your wildcat wells and all that, what we call the exploration wells, the data from the exploration wells will be used. If you want to further develop that asset or the field or the block, you now bring in your well data you have drilled, use your wildcat wells or your wild exploration wells. You now bring them into your time migrated data and do a depth migration. So you have a better imaging of the subsurface that has a better resolution than the time migrated data. So your wells will be your control, just as I've said before. And if you're also in the production stage, after development of the field, if you're not in production, let's say you have done production for a while, you need to also do your depth migration, because at depth migration, you have a better clarity. Sometimes at time migration, you may not even see some structures clearly. Some faults will not be properly resolved because the velocities, you had the velocity limitations. But after you do your depth migration, where you now have wells for controlling the velocity distribution in the subsurface, some structures will now show better. And so if you have a reservoir and the reservoir is not properly draining, in terms of the well you put in the reservoir is not properly draining, it is that your depth migrated data that you see that inside the reservoir there's another micro fault or smaller fault that your time migrated this data set may not have seen because of your velocity limitations during processing. So that is that for my seismic process. And I think I'll call it a day, yeah? I think so I've also thrown a little light to you on what processing is all about. And so in our subsequent classes, we will now talk about interpretation. I think one thing I forgot to add here is deliverables for seismic processing. I'll attach that before I send the slides to you by Monday. So there should be a deliverables. So after processing, in terms of deliverable, is that so the data set that the processing company has to deliver back to the exploration and production company. So such data sets are your stack sections, your CRP gathers, your angle stacks and all that. So I need to add those deliverables to this presentation to, I think, somewhat make it more complete. So yeah, you have an idea of the different data sets that will be delivered to you after processing. So at this point, I would like to call it a day for our lectures today. Don't know if we have any question.
Okay. Does anyone have any question? Okay. Since there's no question, that's all for today. On behalf of everyone, thank you, sir, for this wonderful session. Thank you very much. So you said you were going to add some.
Yes, I'll add deliverables. I'll add it. It's self-explanatory. It doesn't require much explanation.
Okay, sir, no problem. Thank you very much, sir. We really appreciate you.
Okay. I've not seen any response on the last assignment. Did anybody attempt it?
Okay, let me send mine now. I attempted it.
Okay.
Let me send
Okay.
mine.
Okay, no problem. Okay. With this, I think I will call it a day. From next week, we'll start looking at what interpretation is all about. Okay.
Okay, sir.
Thank you. Thank you so much.
Thank you very much, sir. Have a wonderful day.
And you too. Bye.
Okay, thank you.
Thank you so much, sir.
Thank you all. Thank you, everyone.
Thank you so much, sir.
So, my fellow mentees, have
Thank
a
you, sir.
wonderful day. Stop recording.